is Michael Weiß, Senior Account Manager, and I will give you an insight how important it's testing in SIL4 projects. So, who is Hitex? Here you see our location in Karlsruhe, where we have moved 1 month ago, and we are focusing on functional safety, embedded security, engineering in consulting, testing and verification, and delivering of development and software quality tools. And last but not least, we have production as well. We have a global setup with our partners worldwide, and since 2003, we are part of the Infineon Group. Hitex has a large expertise out of customer projects. We are not only focused in one industry, we are focused on various industries wherever functional safety and embedded security is needed. So here you see an overview of a project we have done in the past, like safety integration, certification, emulators, functional safety process consulting, ECUs for powertrain combustion engine. But today we are more focused on the e-mobility world, like DC-DC converters, e-drive development, and battery management. And today I will give you an insight in a project we did for railway signalization. Before I start, I have 3 theses. The efforts for requirements according to high-end safety standard ASIL-D, SIL4 are often underestimated, especially the effort for process documentation and test and verification. Second, testing is started too late. Third, and the management awareness is more on function. Why can't we release it? It works. Give you a project overview. What did we done? We have a safety controller for railway signaling system. It's according to the standard CENELEC SIL4. We have 2 ORIX controllers which monitor each other, and the standard requires for greater SIL3 a minimum of a 2002 system architecture. So here the ORIX is an automotive safety controller, and we had a lot of discussions with the certification authority, in this case the TÜV, that is this ORIX is available or suitable for CENELEC SIL4 as well. As you see, we have chosen 2 different ORIXs, one ORIX TC3 and one ORIX TC4, and we have chosen 2 PMICs for the watchdog, one TLF 35584 and one TLF C55A5. And that's we made for different controllers and PMIC bytes to mitigate the common cause failures. The system receives messages from an Profi safe bus. Both controllers decide the action for their own, and only if both results are equal in a limited time frames, signals will be set. So it's a fail-safe solution to the ORIXs monitor each other, and it's a solution for safe controlling of the communication in a signaling installation. What were the project key facts? Hardware and software development of the safe controller board was done by Hitex according to the railway standard EN 5012X CENELEC SIL4. We had continuous support by the TÜV throughout the specification, development, and verification process. We had about 150 system requirements. There we had about 300 software requirements in terms of architecture, and more than 500 test requirements, so positive and negative tests as well. So having a look on the ratio of the total effort, we had 1/3 specification and implementation, 1/3 documentation and process-related documents, and 1/3 of verification. Yes, I see often in my work with other customers that they underestimate the effort for the documentation and the verification in a high-end functional safety projects. Why 2 RX controllers for SIL4? So here's an excerpt of the EN 50190-29 2080, and here you see the requirements for SIL3 and SIL4, and here 2 different controllers are mandatory. What's about the effort from SIL0 to SIL4? As you see, here we have the project manager, we have the assessor. So integration test verification, and validator can be in one team or one person. Starting to SIL1 until 2, these roles are divided. And starting to SIL3 and SIL4, you have different roles, and here the validator will not report to the program manager. And that increases the effort because you have more effort in the processes, in the team setup, and so on. SIL4 estimation in verification path. The standard required much more different test techniques to respect for SIL3 or SIL4. So here's an excerpt of the standard as well. And it means with an required 2002 architecture, there's a higher complexity and components into the system, which has to be verified and handled. Our first recommendation: to early involve the certification authority in the whole process. So in our case, it was the TÜV Süd. We had large discussions with the TÜV about the system concept and the test concept before we start with the system specification and the tests. So the TÜV approved our concept and our test concept, and we could be sure that this system design with 2 RXs will be accepted by the TÜV. Then we did a system specification and the architecture. There was another round with the TÜV who validated our architecture. Then we did the detailed design, the implementation, unit testing, integration testing, and system testing. And after all, TÜV will certificate the system before we can do the production. So we had a very tight connection to the certification authority, and that's our recommendation. In such high-level functional safety projects, please involve the certification authority as early as possible. Our second recommendation: start with tests and verification as early as possible. So this picture shows the cost to fix a fault. If you find in the implementation, the costs are relatively simple. If you find it in the unit test, the cost will be higher because then maybe you have to change your requirements and you have to track the reason why you have changed requirements. If you find it in the integration tests, you have higher tests. If you find it in the final system tests, and then you have a fault, which you go back to the implementation, then you have a lot of processes to fulfill, and you have a lot of costs to fix the fault. And the worst case is, after release, if a customer finds a bug and you have to recall the application you have brought to your customer. So the later you find bugs and lags in the architecture, the more it's a waste of time and money. How to start test and verification in the development. Here you see a typical development process for embedded systems. We have drivers, we have hardware-related software components, we have software components and application. And normally we start on an evaluation board because the final ECU is in development. After the final ECU is available, you will port all the software from the evaluation board to the ECU. Normally, you do unit tests, and when the ECU is available, you do the HIL tests and the system tests. And what we see at our customers is that 95% of embedded projects are not tested in early phases. And that was the reason why we looked for a system which gives us the chance to start as early as possible with hardware integration tests. And our recommendation is test all parts of the software early in the project, alone and in your team, and automate your tests with continuous integration. And that's our recommendation, our third recommendation. Start early hardware in the loop tests on your desktop. So you see the solution we have chosen for this project. It's a mini HIL from Protos. It's a small board like the size of a laptop. Having a good test and verification concept is essential. The test concept should be approved in an early state by the certification authority. Involve your test and verification team at the beginning of your project. Start defining tests and performing tests at the development time. Achieve your required performance test with mini-HIL. Do not accept self-made test environments, e.g. with evaluation boards from developer. So that's what I see the customers very often, that developers will set up their own tests with evaluation boards or self-built hardware. It's better to support your developers with an early functional test environment for everyone. You can use later in a continuous integration environment and maybe in the end-of-line tests as well. Use the same test environment over the entire project period. Change requests, yes. Fast modification or implementation of the new test cases possible. And please be aware to have a tool qualification for your test environment, in this case for the mini-HIL. Do not underestimate the effort for tool qualification if your tool don't have one. So it's a large effort to have a tool qualification afterwards. Our fourth recommendation, automate your test in terms of continuous integration. So here's a picture of our test system we have set up for this project. We see here several mini-HIL boards with the target hardware, and every developer has remotely access to these test setup. And here we can automate it, build, test, and deliver continuously. And every change, let's assume, has about 5 to 60 minutes. So you have a very fast feedback, and you can test and maybe change your software. So our recommendation is test for every code change of every developer for every project within minutes. That was our choice for a suitable test and verification environment. The mini-HIL board from Protos, which comes with an GUI and model-based language, like you can define your tests and your test structures. Your generated tests, compile it and flash it to the test device. So here on the board is the test controller, is an STM7 2-core controller. Here you see a device under test. You run it, you can connect the in and output pins from the test controller to the device under test. You can log and evaluate. You find maybe some faults in your software. You report, learn about the reports, can iterate, and that's a continuous iteration from generating tests, testing, logging, and changing. The software is Eclipse-based. It has Gradle-based automotion in the background. A model-based test came framework. The open source eTrice is used for simulation models. It's continuous integration ready and has a lot of tracing and reporting tools. Why have we decided for Mini-HIL? Because we wanted to have access to very near to the CPU, to the I/O pins and so on. And the system gives us a collection of a lot of standard interfaces and software adapters, documentation and examples, and up to 200 I/O pins with one board. And it's extendable with an FPGA for fast tests. Here are the key features. The HIL processor itself is an STM32H7 with diverse I/O port expanders like 16 digital outputs, 16 digital inputs, 16 analog inputs, direct I/Os, others I/Os, and connectors. So it's a very versatile system we used in our test environment. Here you see our test setup in our project. In the middle, there's the Mini-HIL with the connection to the device under test. So the device under test is the safe board. You have seen some slides before. We had a programmable power supply, which will be controlled by the GPIO as well. We have an optional network access for the measurements. And we have here the PC who controls the board, where you define the test, where you execute the test, and where you have the reports as well. My conclusion about budget, about your team, about the standards. A high-end safety project according to CENELEC SIL4, IEC 61508 SIL4, or ISO 6262 ASIL-D is a real challenge. Use your know-how and experience in functional safety projects. Set up a well-defined development process, define clear roles and responsibilities in the whole team, have a clear test and verification strategy from the beginning, and use tools that increase your productivity. So don't start with such a high-end functional safety process if you don't have enough experience in this setup. Don't underestimate the specification and requirement phase, the process-related documentation requirements of certifier, and last but not least, don't underestimate the test and verification effort, and choose the right tools which really helps you in the projects. Okay, this was an overview over the project and how we have to solve the problem of test and verification.